Question 26a. The graph below shows a plot of t square against r cube using the data of the inner planets of our solar system. Determine the slope of the graph shown below and use it to find the mass of the sun. So here in this question, we have a plot of t square versus r cube, where t is the orbital period of a planet and r is its average distance from the sun. And in the first part of the question, they want you to find the slope of the graph. Now we can find the slope of the graph by the rule y2 minus y1 over x2 minus x1, where x1, y1 and x2, y2 are any 2 points on the graph. So let us choose any 2 points on the graph. Let this be my first point. The x value over here is 0.4. Now when you're choosing the x and y coordinate, you also have to take into consideration the power on the axis. So I multiply 0.4 with 10 to the power 34. The y value here is around 1.2 times 10 to the power 15. I will call this x1, y1. Then we choose another point on the graph. Let this be the point. The x value here is 0.9 times 10 to the power 34. And the y value is 2.7 times 10 to the power 15. I will call this x2, y2. Now let's substitute this to calculate the slope. Y2 is 2.7, Y1 is 1.2. And since they both have the same power, I can take it outside the bracket, 10 to the power 15 over x2 is 0.9 and x1 is 0.4. And again, they both have the same power, so we keep it outside the bracket, 10 to the power 34. And when you solve this, you get the slope of the graph to be equal to 3 times 10 to the power negative 19 seconds squared per meter cube, where second squared is the unit of the quantity on the y-axis and meter cube is the unit of the quantity on the x-axis. The second part of the question wants us to find the mass of the sun using the graph. So we are going to use Kepler's third law as well as the information on the graph to solve this. We know from Kepler's third law, the ratio of t squared over a cube is a constant, where t is the orbital period of the planet and a is its average distance from the sun, which in the graph is given as r. So I can rewrite this as t squared over r cube is a constant, and that constant is 4 pi squared over gm, where g is the universal gravitational constant and m is the mass of the sun. Let me call this equation 1. Now when we were solving for slope, we know we can find slope by taking the ratio of the y values over the x values. So here from the graph, the value on the y-axis is t squared, whereas the value on the x-axis is r cube. So when you compare this to equation 1, you will notice that t squared over r cube here is nothing but the slope of the graph. So let us substitute this in equation 1. We get t squared over r cube as the slope equals 4 pi squared over gm. We need to find the mass of the sun, so we can rearrange the term over here to calculate the mass. I will move mass on the top here and bring slope down. So we get m equals 4 pi squared over g times the slope. Now let's substitute. M will be equal to 4 pi squared. Universal gravitational constant capital G is 6.67 times 10 to the power negative 11. And this number remains constant for all planets. It's a universal constant. Slope we found to be 3 times 10 to the power negative 19. And when you solve this, you get the mass of the sun to be equal to 1.97 times 10 to the power 30 kilogram. Next, part B. The graph below shows a plot of t square against r cube. Using the data of the inner planets of our solar system, determine the slope of the graph shown below and use it to find the orbital period of Neptune given its radius of orbit is 4.5 times 10 to the power 12 meter. So here in this question, they have given us the radius of orbit for Neptune, which I will write as Rn, and that is equal to 4.51 times 10 to the power 12 meter. And I need to find the orbital period of Neptune, which I will write as Tn. The first part of the question wants us to find the slope of the graph. And we know that we can find slope by taking y2 minus y1 over x2 minus x1, where x1, y1 and x2, y2 are any 2 points on the graph. So let us first choose those 2 points. Let's say I'm going to choose my x1, y1 over here. X value here is 0.5. And when you take the value of x, you have to ensure that you multiply with the power over here. So times 10 to the power 34. Y value is 1.5 times 10 to the power 15. This will be my x1, y1. Then we choose the second point on the graph. Let me choose this one here. X value here is 0.9 times 10 to the power 34. And the y value is 2.7 times 10 to the power 15. I will call this x2, y2. Then let's substitute this to calculate the slope. Y2 is 2.7, y1 is 1.5. Both of them are multiplied with 10 to the power 15 over x2 is 0.9 and x1 is 0.5. And they both are multiplied with 10 to the power 34. And when you solve this, you get the slope to be equal to 3.0 times 10 to the power negative 19 seconds squared per meter cube. Then in the next part, they want us to find the orbital period of Neptune from the graph. So we are going to use Kepler's third law as well as the graph over here to find it. We know from Kepler's third law, the ratio t square over a cube is a constant, where t is the orbital period of the planet and a is its average distance from the sun. Here the average distance is written as r, so we will rewrite this expression as t squared over r cube. Now if this ratio t squared over r cube is a constant, that means I can take any 2 planets, and when I take the ratio of their orbital period squared over their distance of the sun cube, those 2 values must be equal. So if I have planet 1 and planet 2, I can write t squared for 1 over r1 cube is equal to t2 squared over r2 cube. So here in our problem, we can rewrite this as t1 squared over r1 cube. And the other planet, we will take Neptune because we need to find the orbital period of Neptune. And I will write this as tn squared over rn cube. Now to solve this, we need to know the orbital period and average distance of one planet in order to calculate for the other. So how do we find t1 squared over r1 cube? Now when we were finding the slope, we know that slope is given as the ratio of values on the y-axis over the values on the x-axis. Here along the y-axis, we have the values of t squared, whereas on the x-axis, we have r cubed. So t squared over r cube is equal to the slope of the graph. And since this ratio is constant for all values, I can write t1 squared over r1 cube to be equal to slope. So let's substitute that. In place of t1 squared over r1 cube, I will write the slope. So we get the slope of the graph to be equal to tn squared over rn cube. Then we rearrange this term to write in terms of tn. We get tn squared equals the slope times radius cube. That will give me tn to be equal to square root of slope times Rn cube, where Rn is the orbital radius of Neptune. Now substitute the values. We get square root. Slope is 3 times 10 to the power negative 19. Rn is 4.51 times 10 to the power 12 and the cube of the whole thing. That gives you the value of Tn to be equal to 5.25 times 10 to the power 9 seconds. Now this is the orbital period of Neptune in seconds, and we are going to convert this to year. Now how do you convert this to year? We write Tn equals 5.25 times 10 to the power 9. We know that a year has 365 days, and every day has 24 hours, and every hour has 60 minutes, and every minute has 60 seconds. So anytime you want to convert from seconds to year, you have to divide by this conversion factor. So that gives you the orbital period of Neptune to be equal to 166.5 years.